Hello. In the last class, we have discussed the principle of wave-particle duality and how this principle can explain the wave properties of particles and particle properties of waves. The main result of the last lecture, the two main results of the last lecture were the relation between energy and frequency of a wave/particle. Namely, energy is frequency times Planck's constant, E equals hf. And the second relation was the de Broglie's formula for the wavelength of a particle having momentum p, namely the wavelength lambda is Planck's constant h divided by particle's momentum p, in magnitude of the particle's momentum, of course. The wave-particle duality was able to make a prediction that could be experimentally tested. Namely, if you send a beam of electrons, for example, electrons, having the same energy onto a crystalline surface, then the crystalline surface will act as a diffraction grating. So depending on the angle at which you are detecting the reflected electrons, you will observe either minima or maxima of the electron flux. And today I will describe another spectacular success of the wave-particle-based description of nature. Namely, it is Bohr's model of hydrogen atom. Then I will tell you in what respects this model is not quite complete, how it should be expanded. I will need to introduce the concept of the wave function. A wave function is a complex valued object, and so I will have to tell you a little bit about complex numbers. And I will also tell you how the wave function can solve some of the difficulties of Bohr's model. So let's begin with hydrogen. Today we know that that atoms consist of positively charged nuclei. They are very small, very heavy as compared to the electrons. And around those nuclei, electrons are orbiting. So that's the standard picture. This picture was established by Ernst Rutherford in the beginning of the 20th century. And Niels Bohr used this picture to understand the emission spectra of hydrogen. So it was known well before Niels Bohr in the late 19th century, when people developed the spectroscopic methods, that gases, when they are excited, for example, when the electric current is flowing through a gas, gases emit light, and that light has not continuous spectrum, but it has discrete spectrum. So it has certain emission lines, emission frequencies, better to say frequencies. So the frequencies found in the spectrum of hydrogen are well described by an empirical formula introduced by Johannes Rydberg in 1888, so 25 years before Niels Bohr published his model. And Rydberg's formula tells us that the frequencies of emission of hydrogen, atomic hydrogen, are a constant, which is 3.29 10 to the 15th hertz, times the difference of inverse squares of two positive integers, 1 over n1 squared minus 1 over n2 squared, where n1 and n2 are positive integers, and of course n2 must be bigger than n1, so that this difference is positive. Niels Bohr applied the concept of de Broglie's wavelength, lambda equals h divided by p, to the model of hydrogen suggested by Ernst Rutherford, in which an electron orbits around a positive nucleus, which is just a proton. And so he wrote down two equations. Well, I'm not actually following the historical presentation of Bohr's model as presented by Niels Bohr himself, but the presentation that I will show in this slide is mathematically equivalent to Niels Bohr's presentation. So Niels Bohr wrote two equations. One equation postulates that so if you have an electron moving on a circle, and there are two forces acting on the electron, which are the centripetal force. This is just the Coulomb interaction between the electron and the nucleus, and the centrifugal force, which pushes the electron away from the nucleus, radially. And the electron moves on the circle because these two forces perfectly balance each other. So Coulomb's force, centripetal force, is Coulomb's constant, Ke, 8.99, 10 to the 9th Newton per Coulomb squared times meter squared. Newton meter squared over Coulomb squared. Product of electron and nuclear charges, both are elementary charges, so E squared, E is 1.602, 10 to the negative 16th coulombs, divided by the radius of electron orbit, that is the distance between the electron and the nucleus, divided by r squared. So that's Coulomb's law. And now the centrifugal force is known from elementary mechanics. It's mass times velocity squared divided by the orbit radius squared, or momentum squared divided by the product of mass and orbit radius. So that's the first equation. In this equation, we have two unknowns: electron momentum and the orbit radius, P and R. We need another equation. That second equation is the resonance condition, which says that the circumference length, that is the length of the orbit of the electron, must accommodate an integer multiple of electrons' de Broglie's wavelengths. 2 pi r, circumference length, is n lambda, where lambda is the ratio of Planck's constant h to electron momentum p. So now we have two equations: force balance equation and the quantization condition. 2 pi r is nh over p, which we can solve for the two unknowns r and p, and I drop the details. Here are the expressions for momentum and orbit radius r. And both momentum and radius r depend on this integer, positive integer number n. Now we can plug in this momentum and radius into the expression for the electron energy. Electron energy consists of two parts: kinetic energy, momentum squared divided by twice the electron mass, and potential energy, which is minus the Coulomb's constant, elementary charge squared, divided by the radius of the orbit. So plug in the expressions for P and R into the energy formula, and you will find that energy is quantized and that the energy expression is negative constant, which we called Rhe for Rydberg. It is called the Rydberg's constant, divided by the integer n squared. And this Rydberg's constant is a combination of fundamental constants: Coulomb's constant, electron charge, electron mass, and Planck's constant. So this is this combination. If you plug in all the numbers and convert the energy from joules into electron volts, you will come up with 13.605, well, 13.6 electron volts. Now, as an electron makes a transition from some higher energy state, large n, to some lower energy state, smaller n, its energy changes by the amount which can be deduced from this minus Rydberg's constant over n squared. So it is minus Rydberg squared, minus Rydberg's constant, 1 over n initial squared, minus 1 over n final squared. So that's the change of the electron energy. This electron energy is released in the form of a photon. So the photon energy is given by the same expression: Rydberg's constant times the difference of two of the inverses of two integer numbers. Divide the photon energy by Planck's constant, you will get the photon frequency. And it turns out that the ratio of Rydberg's constant derived within Bohr's model of hydrogen to Planck's constant is exactly 3.29 10 to the 15th hertz, as found by Johannes Rydberg 25 years before Niels Bohr. This success is spectacular. Bohr's model worked extremely well for hydrogen, but it had some problems. And here are some of them. The first problem is this. So de Broglie's expression for wavelength works for a particle which is actually free. A free particle flying in vacuum in outer space, for example, but an electron orbiting around the nucleus is not a free particle. So strictly speaking, we have no right to apply de Broglie's expression for electron wavelength, or we should be careful applying this expression. In this case, in the case of hydrogen, we did get, together with Niels Bohr, we did get the correct form expression for the electron energies, but maybe it was just luck. Maybe there was no particular reason, no good reason to apply de Broglie's formula. The second problem is this. All right, okay, so we have found the allowed quantized radii of the electron orbit. But still, when an electron orbits, moves on a circuit, circular motion is the type of accelerated motion. Because acceleration is when a particle changes its velocity, either in magnitude or in direction, when the particle moves on a circuit, on the circle. Even though the velocity of the particle doesn't change in magnitude, the direction of the velocity changes. So it is a type of accelerated motion. From electrodynamics, we know that when a charge is accelerated, it emits electromagnetic waves. So the electron should actually be constantly emitting electromagnetic waves, not moving on an orbit of constant radius, because electromagnetic waves carry away energy. So as the electron moving, circling around the nucleus emits electromagnetic waves, it should constantly lose energy. The radius of that orbit should constantly change. It's unclear why electron orbit of radius predicted by Bohr's theory, this radius should be stable. So that's the second problem. Then there were more problems. For example, when Niels Bohr tried to apply this same reasoning to a more complicated atom, helium atom, 2 electrons orbiting around an alpha particle, 2 protons and 1 neutron, it didn't work. He couldn't correctly reproduce the emission spectra of helium. So Bohr's model is, I wouldn't say it is wrong. I would say it is incomplete. It needs to be extended somehow, or maybe we need to adopt a different view of particle waves. So, and this view has been developed indeed in 1920s, and it is based on something called the wave function of the electron. Now, a wave function, before we start discussing wave functions, let me tell you this. A wave function is a complex valued function of position and time. So we need to talk about complex numbers. So let's do that. Complex numbers. A complex number is an extension of the concept of a real number. Now, a real number includes integers, positive, negative, zero, all rational numbers. Rational numbers are the ones that can be represented as ratios of integers, and irrational numbers which cannot be represented as ratios of integers, such as square root of 2 or pi or the number e, 2.71, and so forth. A complex number is a pair of two real numbers. So x and y, and it is written as z, complex number z is x plus y times I, where I is a very special number. It is called the imaginary unit. It has a special property. If you square the number I, you will get -1. It's impossible for real numbers. So x and y are real numbers. Y is the so-called imaginary number. And z is a complex number. So do we observe, can we measure anything in real life as a complex number? No, we cannot. All measurements that we perform in real life are expressed as real numbers. Are complex numbers useful? Extremely. They are used in the analysis of electrical circuits, for example, the concept of complex impedance, in the analysis of mechanical motion, and in quantum mechanics, of course. So, all right, so if you have a complex number, it has a real part, x, and the imaginary part, y. Now you can define arithmetic operations between complex numbers, so you can add them or subtract them. When you add two complex numbers, you add up their real parts, and that will be the real part of your result. You add up the imaginary parts of the two complex numbers, that will be the imaginary part of your result. Now you can also multiply two complex numbers, following the usual rules of multiplication of a sum times another sum. So a sum of x1 and y and I y1, and the sum x2 plus I y2. Just keep in mind that y squared is -1. So what you get is x1, x2 plus I y1 times I y2, but I times I is -1, so you have minus y1, y2. And that's your real part, x1, x2 minus y1, y2. And the imaginary part, I y1 times x2, I y2 times x1. That's the imaginary part here. The next operation is the so-called complex conjugation. Just flip the sign in front of every imaginary unit that you encounter in your complex number. So if the complex number is x plus I y, then the complex conjugate of that number is x minus I y. Now, why do we need this operation of complex conjugation? In order to introduce, for example, introduce a further arithmetic operation, the division of complex numbers. Before that, if you multiply a complex number by its complex conjugate, you will get a real number, x squared plus y squared, sum of squares of the real part and the imaginary part. Now the division of complex numbers. Let's say one complex number is divided by x1 plus yi1, iy1 is divided by another complex number, x2 plus iy2. What's the result? You have a complex number in the denominator, but we would like to divide by something which is real value. That would be more clear. All right, so, but we already know how to convert a complex number into a real number by multiplying it by that number's complex conjugate. So let us multiply the numerator and the denominator by the complex conjugate of the denominator. Then in the denominator, you will get a real number, x squared plus y, x2 squared plus y2 squared. And in the numerator, you get a product of two complex numbers, x1 plus iy1 and x2 minus iy2 complex conjugate of z2. And we already know how to multiply two complex numbers. So that's the rest of this operation is relatively easy. So the real part would be x1, x2, plus y1, y2, because notice that here this plus, here is minus, but then we have I squared, which is -1. So minus times minus gives me a plus. And here is the imaginary part. Now I would like to introduce something called Euler's formula. Extremely useful in complex analysis. Let us consider a special complex valued function of a real valued argument, which I call theta. So this complex valued function f of theta is written as natural logarithm of cos theta plus I sine theta. Okay. Now let's take the derivative of this function with respect to theta. And we differentiate natural logarithm, sine and cosine using the usual rules of differentiation. We know how to differentiate those functions. For example, the derivative of natural logarithm is 1 divided by the argument of natural logarithm. So using the chain rule, the derivative of the logarithm of cos theta plus I sine theta is 1 divided by cos theta plus I sine theta. That's the derivative of the natural logarithm. Now we need to differentiate the argument of the logarithm with respect to theta. Cos theta after differentiation gives me a negative sine theta. Sine theta gives me cos theta multiplied by I. And now I see that the numerator and the denominator are, they look pretty similar, but not quite. But if I multiply the numerator by I, and the, oh no, if I recall that negative 1 is actually I squared, then I get I squared sine theta plus I cos theta. And now I see that the numerator and the denominator differ by a factor of I, imaginary unit. So take I in the numerator outside of the brackets, you get I times cos theta plus I sine theta, which is the denominator. And so the ratio is just this number I. So this function, this specially chosen function, is I theta plus the initial value of this function when theta is set to 0. So setting theta to 0, you get natural logarithm of cos 0 plus I sine 0, but sine 0 is 0. So, and cos 0 is 1, and natural logarithm of 1 is 0. So we find that this function is just I theta. The initial value, f of 0, is 0. F of theta is I theta. So natural logarithm of cos theta plus I sine theta is I theta. And finally, we exponentiate both sides of this expression, of this equation, and we prove Euler's formula. E to the power I theta is cos theta plus I sine theta. Interesting, isn't it? What can we use Euler's formula for? For an alternative representation of complex numbers. A complex number is real part plus imaginary unit I times the imaginary part. But also we can now write a complex number as the modulus. It is the so-called polar representation. Modulus times exponential to the power I theta. And the real part, and if you apply Euler's formula to this exponential to the power I theta, you will find that the real part is modulus times cos theta, and the imaginary part is modulus times sine theta. Now, the modulus of a complex number is square root of x squared plus y squared. Square root of the real part squared plus the imaginary part squared. And the phase angle theta can be found if you divide the imaginary part y by x. You will get that tangent theta is y divided by x. So the phase theta is inverse tangent of y divided by x. Now notice that there are special values of this exponential to the power I theta, cos theta plus I sine theta. If theta is an integer multiple of 2 pi, then cos 2 pi or cos 2n pi, where n is an integer, is always 1. Sine of 2n pi is always 0. So e to the power I times 2n pi, where n is an integer, is always 1. If the integer is odd, if the integer is odd, 2n plus 1 pi, then cos 2n plus 1 pi is -1. So this exponential to the exponential of I times an odd integer multiple of pi is -1. If the angle theta is pi over 2, then this exponential will have the value plus I, imaginary unit, because for theta equals pi over 2, cos pi over 2 is 0, and sine pi over 2 is 1. If theta is negative pi over 2, or if theta is 3 pi over 2, this exponential, e to the power I negative pi over 2 is negative I. Okay. So now you know everything that you need to know about complex numbers, and we can move further. So a wave function, let me just say what a wave function is. A complex valued function of space R and time t. It has a real part and imaginary part. And you can write it like this in this form, or you can write this as modulus of the wave function, modulus psi, times exponential to the power I theta of R and t. And the fundamental postulate of quantum mechanics is postulate, something which cannot be reduced to more fundamental principles. Okay, so a fundamental postulate of quantum mechanics is that the wave function gives you, it doesn't, by itself, it doesn't have a physical meaning, but its modulus squared, this modulus squared, whatever multiplies the exponential, is the probability density to find the particle near a particular point R at the moment of time t. So if you imagine, so let's say you have an electron, and it is described by a certain wave function. Like, you do not know what it is, but it's not important right now. Imagine a small volume dV around the point R. The probability to, and we ask ourselves, let's say I want to determine where the electron is located. So I somehow perform a measurement of the electron's position. What is the probability that I will find the electron in that volume dV around the point R? The answer, modulus psi of RT squared times dV. That's the probability. And psi squared, modulus psi squared, is the probability density. Now, at least in principle, you can measure the probability density, but the phase is unmeasurable. That's another postulate of quantum mechanics. Probability density, modulus squared of the wave function, is measurable, but the phase of the wave function is not measurable, unmeasurable. So you can call the modulus of the wave function the body, and the phase of the wave function the soul of the wave function, and become very religious, or just use it as a figure of speech, whatever you like. By the way, this distinction between the body and the soul of the wave function is not my invention. It was I heard it from my own physics professor who taught me quantum mechanics about 30-something years ago. And I find it nice and apt. All right, now, normalization. So since the wave function has the physical meaning of probability density, it must be normalized. Not the wave function, the modulus squared of the wave function has the physical meaning of the probability density. It must be normalized, which means that if you integrate the probability density over the whole space available to your particle, for example, electron, you will get the total probability to find the electron somewhere in that space available. And that total probability is 1 because we know that the electron exists somewhere. You do not know where it is. It is somewhere. So this means that the volume integral of the modulus squared of the wave function must be 1. Sometimes, the electron is confined to two-dimensional motion, in which case its wave function depends not on 3 arguments, x, y, and z, well, plus time, but on 2 space arguments, x and y. And by the way, in that case, the wave function will be measured in different units than in 3 dimensions. And the normalization condition on the wave function will be that the wave function of x and y modulus squared, when integrated over the area available to the electron, should give you 1. Or the electron might be confined to 1 dimension. For example, an electron bouncing between 2 walls. Yeah, it is performing 1-dimensional motion, in which case the wave function depends on just 1 argument, let's say x, and modulus squared of the wave function integrated over the spatial coordinate x should give you 1. All right. All right, so and the wave function depends on space r and time t. There is a special class of wave functions, the so-called, which correspond to the stationary states, stationary wave functions. A stationary wave function are not time independent. They do depend on time, but they depend on time in a special way, in the form of exponential to the power I or negative I omega angular frequency times t, where the angular frequency is, of course, related to the energy of the particle divided by Planck's constant, h bar. These states are stationary in spite of the fact that the wave function depends on time. It oscillates. It's exponential to the power negative I omega t, can be written as cos omega t minus I sine omega t. So it is an oscillating factor. But since the phase of the wave function is not measurable, and only the modulus squared, modulus of the wave function is measurable, notice that the modulus of the wave function is time independent. So the total position and time dependent wave function is the product of the position dependent part, which I write as capital psi, and it is a function of position r. And the time dependence enters in the form of this exponential to the negative I omega t. Modulus squared of this wave function is just position dependent part modulus squared. And it is time independent. Modulus squared is time independent. And because it is the modulus squared of the wave function, which is the only measurable part of the wave function, it is for this reason such a wave function describes a stationary state. Now, since the modulus squared of the wave function, it can be associated, it is directly proportional to the charge density of the, let's say this wave function describes an electron in an atom. And if you multiply modulus squared of the electron wave function with the electron charge, negative elementary charge, you will get the charge density associated with that electron. Now, if the electron finds itself in a stationary state, then this charge density does not change in time. There is no acceleration of the charge associated with the charge density. And if there is no acceleration, it means that this electron is not radiating electromagnetic waves. And so we have solved one of the problems pertinent to Bohr's model, that orbiting electrons should be emitting electromagnetic waves. No, they should not, because electrons are in stationary states. The charge density doesn't change. It only remains to figure out those wave functions in the stationary states. But how do we do that? And we will discuss that in the next lecture. For now, thank you all for your kind attention.